Hello. My name is Warren Henning. I'm a student here at UCSD. I'd like to talk to you about a quirky new library for Ruby that's come out recently called DRP. DRP stands for Directed Ruby Programming, and I'll explain to you what that means and why you might be interested in it. Hopefully you don't mind that this will be a little light on code samples. I'm going to try to talk more about motivation, background, and so on, because actually, fortunately, DRP has very good documentation, but it kind of assumes you have some background, so this will hopefully kind of fill you in as to what this is all about. So this might not seem directly relevant to web programming, but I'll try to explain some possible points of connection. So what this is about is something called evolutionary computation. I'm going to be talking about genetic algorithms, genetic programming, grammatical evolution, and then DRP builds on those. Oh dear, the text is a little bit smushed, but whatever. What is evolutionary computation? Well, evolutionary computation is a biologically inspired way of doing optimization. So you might wonder, what exactly do I mean by optimization? So that means minimizing or maximizing something. So you're always working with a function that measures how well or how poorly you're doing something. Like, for example, say you're trying to build a spam filter, then you want to minimize the amount of spam that gets through, and you want to minimize the number of false positives. Generally, optimization is always talking about minimization only, because maximization and minimization are basically the same thing. For instance, winning a game as often as possible is equivalent to losing as little as possible. So so you can talk about optimization as minimization without loss of generality. So this function that we're working with, we call it an objective function. And the important thing is that you make very few assumptions about this objective function. Classical means of doing optimization usually make some fairly restrictive assumptions about what this objective function is. Oftentimes they assume, like, there are special techniques for when it's linear, when it's quadratic. Most of them generally assume that it's at least a nice mathematical function, that it's differentiable or continuous or whatever. Evolutionary computation doesn't assume any of that. It could be, it could be readings from some kind of machine, and it could be like video sensors or something that's not at all nice and clean. So what do you do if you can't assume a nice mathematical structure? Well, what you do, the basic idea is you begin by randomly initializing a set of possible solutions to the problem and then iteratively improve on that. So for instance, say you're working with the special case of a simple function, like say just a parabola, x squared. So you might initialize a bunch of random numbers. To begin with, at first, if you just randomly guess, those aren't going to be very good. Your initial guess isn't going to be very good, but there will be variation. And so you have an iterative cycle where you reward the good solutions, the better ones, and you punish the bad ones. The unfit solutions, the bad ones, will die off, and the good ones will survive. And you modify this set of solutions, which you call a population, using operations that are somewhat like what happens in genetics. The parallel is pretty crude, but you have something called mutation. Like the most common operations are mutation and crossover. So how exactly does this work? Well, one of the simplest family of evolutionary algorithms, and the oldest ones, are something called genetic algorithms. So in genetic algorithms, your solutions always take the form of strings. So usually they're strings of digits. And actually what was done in the past was you would have strings of binary digits, actually. Because, like, say you want an integer solution to a problem, well, it's straightforward to convert, each block of 8 binary digits to an integer. You can also convert them to real numbers or whatever else you need. And so it's like, it's kind of like DNA. You have long strings, except instead of having the, CGAT, you just have 1 and 0. So it's binary rather than like quaternary. So here's an example of doing mutation and crossover on 2 example individuals. These are just parts of it. So this is just done at random. So in mutation, there's a small probability that each bit of each individual would be flipped from 1 to 0 or 0 to 1. So you can see here that in this case, by chance, those 2 ones in red become zeros, and so you just flip them. With crossover, what you do is at some random point, you just basically flip and switch all the parts of those individuals to create 2 new individuals. So what is the point of doing this? Well, the idea is that with crossover, you'll take 2 good solutions and combine them in such a way that's better than each of one of the ones that existed before. So you'll create something even better than what existed before. So you're swapping around potential solutions to a problem. Mutation, because it's a fairly infrequent event, is just induces a little bit of diversity in the population. And so this is all basically stochastic and random. But that's how it works. But DRP doesn't actually work with genetic algorithms. It's more related to something called genetic programming. So in genetic programming, rather than working with strings, what you're actually working with is something that's kind of like actual computer programs. And I don't know if any of you have used the language Lisp, but in Lisp you work with these tree-structured S expressions. All your program code can be expressed in this kind of Lisp form. So you have these tree-structured expressions, and to do crossover and mutation, what you're actually working with is subtrees. So you would swap random subtrees, and here in this figure, what's been selected at random is this part in the lower left. This figure was taken from a 1996 report by a researcher at the St. Louis Federal Reserve by the name of Christopher Neely. He used genetic programming to investigate creating profitable foreign exchange trading rules. That was back in 1996. So here's general pseudocode for just about any evolutionary algorithm. As I said before, you randomly initialize the population, and then you just have this cycle of you evaluate the population, you vary it, and then you select the new population, and so it repeats like that until you decide it's done. Like you might just do it however many times, 1,000 times, 500 times, whatever. So that's kind of how genetic algorithms and genetic programming work. Hopefully this isn't too confusing, but what you may be wondering is like, does this stuff work? Like, can you solve real problems with this? And does anyone use it? Well, fortunately, the answer to those questions is yes. So I'd like to just briefly discuss a couple real-world examples of where this has been used. So this first example is NASA used genetic algorithms to design the antennas on satellites. Apparently, designing an antenna, you can see from the photo by comparing them to the size of a coin that they're pretty small. Apparently, designing these things is pretty much a black art, and even highly skilled engineers don't really know what they're doing. But however, for any particular configuration, like, it looks like a bunch of little pieces of paper clips bent around, you can measure how good that is. And so they figured out some way of encoding a particular how to encode an antenna design in the form of a string of digits or whatever, and then they basically just used these kind of algorithms, and this actually went into space, and it's better than anything a human can design. Another example, using genetic programming. So this is image processing. So the task here is to recognize objects. So this could be like recognizing people's faces in an image. What he chose to work with here is a couple different data sets. The one on the left, you have this noisy image, a black background. You have these circles and triangles, and what you're trying to do is recognize the triangles. And then you can see that the white dots represent recognition. So he basically recognized them, except there's a false positive in the lower right. Similarly, in the image on the right, the task is he has this wooden background, two kinds of pasta randomly spread around. The task is to recognize the long ones. And so you can see by the white dots that he basically recognized them, although again, there's a false positive. So just the point is, this stuff is useful, in real life. And there are a lot of other applications, but most of them are in engineering design. But you guys are basically web programmers, so why should you care about this stuff? Well, I guess mainly because they're useful in machine learning tests. They can be used for data mining. They can be used to create classifiers. Using a kind of related but different set of algorithms that are kind of more inspired by insect behavior, you can do things like clustering. So say you have like all the pages on Wikipedia, and you want to find groups of pages that are similar somehow, like by topic. And so you want to create, an ability to explore these large sets of data, and you want to basically use these large amounts of information profitably. Algorithms like this can be used for that. So what are some ways that you might use such algorithms? Well, one possibility is, as I kind of hinted at with the image processing example, you could do something with, say, face recognition, face detection, which is kind of what, there's a startup called Ria.com, and basically they do human photo search. So you could do something analogous to that. Or, for instance, maybe you're familiar with the social bookmarking website Delicious. So you could build an enhanced version of that where where the user doesn't have to type in tags. The keywords for a web page they enter are automatically extracted. When they enter something, it's automatically classified. They don't have to type in stuff. They don't have to do stuff. They don't have to organize it. It's done automatically. So I think it's kind of interesting, and I think it's worth thinking about. One of the ways that these things differ from other machine learning techniques is that they're scalable. They're basically inherently scalable because of the fact that when you evaluate each of the individuals in your population, evaluating each one of those is independent. So it's like doing a web application. Each HTTP request is independent of all the others. It's a stateless protocol, so that creates the possibility for load balancing. So it's basically what's called embarrassingly parallel, the way ray tracing is, the way other computer graphics tests are, and in my opinion, they're a lot simpler and more intuitive than other machine learning algorithms you might come across. I don't know if any of you have ever heard of something like support vector machines. I've tried to figure it out maybe a dozen times, and I still have no idea what they are. So I'm giving you a lot of background. You just have to kind of be patient. We're getting there. So what DRP is most closely related to is something called grammatical evolution. Excuse me, grammatical evolution. Grammatical evolution basically is a reaction to genetic programming. It takes the opinion that genetic programming has some problems with it. So the main one is that you have no control over the kind of individuals that evolve. So what you want to do with grammatical evolution is you actually have, it's kind of like genetic algorithms in that what you perform the search on is a list of integers. And then this is mapped to create a kind of tree-like structure using a particular algorithm that I'll explain. But you dictate how that is. And so you can precisely control the kind of things that are developed. So I might be running over time, but basically what you do is you look, like say you have this individual here, this list of integers, 220, 203, etc., to 30, and say you have that grammar on the left, which lets you, as you can see, it lets you create mathematical expressions, say. These could be something for face recognition, face detection, whatever you're working with. So what it does is it uses the integers to select which rule to expand out, starting from the start symbol to create a particular individual that you can then evaluate the fitness of. So the way you do that, like say you start at the beginning, this expr thing, you have to choose which of those 4 rules to expand out to. So you have 4 choices, and the particular integer you start with is that one. So at any given point, you decide which one by taking the integer value and then taking that modulo the number of choices, and that gives you the number. That gives you a number, which is the rule you choose, and then you have this iterative process of expanding out the individual until you get an expression, a program, whatever. So you can actually evolve programs in any language. This could be English, Lisp, Ruby, whatever. You could just interpret that with a suitable interpreter, and then evaluate that fitness, and then you can. So this provides a mechanism for evolving programs in any language that you can express as a grammar. So now we can finally explain what DRP is. So basically, the author of DRP notices a problem with grammatical evolution. Namely, it's possible in this mapping process. Here the mapping works out fine, but what could happen is, for instance, if you're repeating, if you start at this first non-terminal, if you keep choosing this particular one over and over, which has you choose more expressions, more exprs, you will never wind up mapping to an individual until you'll get into this infinite loop. So if you're at the end of your list of integers, but you have more non-terminals to take care of, the idea is you wrap around. Well, you only wrap around so many times or else you might never terminate. So the author thinks this is undesirable, and he represents it differently and gives you more control over how you expand out your integers into these structured expressions. So you can, with a little bit of Ruby metaprogramming, you can express maximum possible recursion depths. You can do all kinds of tricks, and the interesting thing about DRP is that it's not a lot of code. It's only maybe a few hundred lines at this point, and that's unusual because using a language like C, C++, Java, implementing even less sophisticated evolutionary algorithms like simple genetic programming, that takes thousands of lines of code. And that's, I can see that's working with pointers. That's just, it takes a long time to debug. So it's pretty interesting. However, DRP might be limited in scope in that it is implemented in Ruby, so it's just not going to be useful for hardcore engineering optimization. Probably its niche is in interactive applications, where to evaluate each individual, the actual fitness function comes from a human. So, like, the author of this intends for it to be used to, like, automatically generate art and stuff. A possible real-world example I heard about in the news recently is what the police in the United Kingdom have, or at least it's being used experimentally. They have a database of images of people, and they use a technique called eigenfaces, which lets you actually generate images of people's faces parametrically. So you plug in a string of numbers, and out comes an image of a person. How they do that, I don't know how familiar you guys are with linear algebra, but it involves computing eigenvectors of something called a correlation matrix. But basically, in comes numbers, out comes a person's face. So that's a numerical optimization problem. So what they do is they sit down someone who has been victimized, and they have them initially start out with these sample faces, and they have them rank them. And so they get say, like, which of these images looks most like the person who committed this crime. So they would rank them, whatever, maybe first, second, third, fourth, fifth out of 5 presented. So it would repeat this process over and over for maybe 5 to 10 minutes, and then the final best individual is used as the sketch you would see on the news or something. And this is actually apparently a lot more efficient and more accurate than the way it's normally done, which is where you select a bunch of facial features out of a book, kind of like building a Mr. Potato Head. So this stuff could actually, so there are potential real applications. And so the point for using it for interactive applications, if the objective function, which is always the bottleneck, is human response, the fact that you're in Ruby or any other language doesn't matter. The process of allocating and deallocating trees in your code or whatever, that isn't the bottleneck. It's always the objective function. And so if that is dependent on how fast a person can rank things, that's going to be equally slow no matter what you implement in. So I think it could be used for all kinds of interesting things. So yeah. And you basically express grammar rules like the grammar I mentioned before. In a typical grammatical evolution system, you would provide something like this in a file. Well, DRP takes a quirky Ruby type approach. You just write pure Ruby code, and then this is actually correct code. You define the same rule multiple times, which it takes care of via metaprogramming going on in the background. So you just write it out in normal Ruby code. The documentation for DRP includes an example of generating like random browser canvas images. These aren't subject to any fitness measurements. It just randomly generates them, which is why these all are pretty much nonsense. But what you could do is hook this up to a genetic algorithm or whatever, or any other kind of optimization method, and then have that set up, that interactive process, and then build a pretty picture, I guess, or something. So basically, what the take-home message is here is that evolutionary computation is useful for solving difficult real-world optimization problems. DRP takes an interesting approach to it, but probably for hardcore engineering optimization, for building a large website that does lots of machine learning and stuff, you might need to use a faster language. So that's about all I have to say. And then these are some resources, and I'll if anyone cares, I'll post the link to these slides. They're actually already up on my webpage. So that's all I have to say. So are there any questions? Yeah.
So the objective function is basically the objective function and your ability to create a grammar that properly represents what you're trying to achieve are two main factors that come up with something.
That is an excellent point. If you measure it the wrong thing, you're not going to get proper solutions. And let me give you a concrete example. One of the main ways that grammatical evolution has been applied is financial stuff. So the people who invented this, they're over in Ireland. They've written papers about creating like stock trading strategies with this. So if you're creating a stock trading strategy, that raises the question: how do you measure how good a particular way of trading stocks or foreign currency or whatever you're trading on the market is? Well, one of the first ideas you might get is, more profit is better, therefore you want to maximize profit. Well, actually, that's not what you want. What you want is consistent profits. You want risk-adjusted returns. So if you don't take into consideration risk, if you measure the wrong thing and you only measure net profit in your trading strategy, then you'll get a trading strategy that is not really safe to use. And so if you measure the wrong thing, and if you don't give it the right building blocks, you don't have a hope of getting it right. So you're absolutely correct.
In the case of doing something like facial recognition, there's still a considerable amount of effort that needs to be done to actually write code that is capable.
Oh yeah, to actually do this, yeah, you'd be writing quite a bit of code. Or you could just use something different, like there's stuff you can download out there. Or you could shell out a few $100s and get something commercial. But it's just an example, because I just try to reach out to you guys. I used this. I implemented grammatical evolution last quarter and used it to build face detection, kind of like that slide I showed several slides back with detecting pasta and stuff, except it was with faces. So what you have is you have this little square, and you move it over the image and you scale it down, and so basically you look for any possible instances of a face at any size. And then what you evolve is an expression that takes in pixels and says whether that's a face or not. So I used it for that, and then I've also experimented a little with trading strategies. But I haven't risked any money on it. But there are interesting results in the literature on that, like beating the market and stuff.
Did you find the faces?
Yeah, I got pretty good results. It runs fast and it's reasonably robust. Under poor lighting, it doesn't work though. But face recognition under poor lighting doesn't work in general. RIA, they started out, they were going to do like Flickr except with like faces and stuff, but they discovered that that's really hard. So they changed the problem, and now they're like, I guess they do face searching or something. Okay, so that's all I have to say. I hope I didn't confuse you too much.
That concludes this episode of the SD.RB podcast. See you next time.